Let's talk about a classic electronics puzzle. How in the world do you get DC power through a transformer? I mean, it feels like it should be impossible, right? We're always taught transformers are AC devices. Well, today, we're going to pull back the curtain on the forward converter. It's this super clever piece of engineering that totally solves this problem, and believe me, it's the hidden hero inside a ton of our modern gadgets, like our PCs and all that telecom gear that needs stable, isolated power.
So here's how we'll break it down. First, we're going to challenge that old belief about transformers and DC. Then, we'll get our hands dirty and build the basic converter circuit. After that, we'll uncover a really big hidden danger and the slick solution for it. And finally, we'll put all those pieces together and see the complete picture.
All right, let's kick things off with Section 1, a DC transformer. We're going to start by poking a hole in a rule that, a lot of us just accept as gospel in electronics. So let me ask you straight up, can you really push DC power through a transformer? I bet for most of us, our gut reaction is, no way. Transformers need a changing magnetic field to work, and DC is just a flat, constant line. It doesn't change. And that gut feeling is mostly right, but it's not the whole story. The common belief is, yeah, transformers are for AC only. But the reality? You totally can transfer DC power. You just have to be tricky about it. You need a clever little switching setup.
So here's the trick. Instead of feeding the transformer a nice, steady DC voltage, you just chop it up. By using a really fast electronic switch like a MOSFET, you're turning that DC on and off super fast. What you get is this pulsating voltage. It's kind of like a one-sided AC signal, and that's something the transformer can actually work with. You're basically tricking the transformer by making the DC look like AC.
Okay, so let's move on and see how this clever trick actually builds the heart of the converter. We're going to go from that basic principle to the actual circuit that makes it all happen.
Now, the forward converter isn't some crazy brand new design from another planet. It's actually just two things we already know, bolted together. First, you've got the transformer, which gives us that super important electrical isolation. And then, get this, the entire output side is just a plain old buck converter, that super common circuit we use all the time to step down DC voltage. That's why people call this a buck-derived converter.
So, how does it all work? Let's just follow the energy. When that main switch is on, bam, voltage hits the transformer's primary coil. A voltage then pops up on the secondary side, and that pushes current right through this inductor. The inductor starts storing up energy in its magnetic field, and at the same time, it's feeding current to our load. Simple enough.
But now, what happens when the switch turns off? The transformer shuts down, no more energy transfer. But that inductor we just charged up, well, it hates sudden changes. Its current doesn't want to stop. So its magnetic field starts to collapse, and that current finds a new loop, freewheeling through the second diode. We call it a catching diode. And this is the magic that keeps a nice smooth flow of current going to our load, even when the main switch is off. Now, for this whole thing to work without blowing up, it has to follow a really important rule called volt-second balance. It's actually pretty simple. It just means that over one complete on-off cycle, the average voltage across that inductor has to be 0. If it's not, the current would just keep ramping up and up and up with every cycle until, poof, something's going to melt. So the positive energy pumped in during the on-time has to be perfectly balanced by the negative energy released during the off-time.
And all of that physics boils down to this nice, clean formula. The output voltage equals the input voltage times D, which is the duty cycle of our switch, times N, the turns ratio of our transformer. Now think about it. If you just cover up the N, you have the exact formula for a regular buck converter. The transformer just gives us another lever to pull, another way to step the voltage up or down, plus that critical safety isolation.
Okay, so this seems pretty solid, right? Maybe a little too easy. There's a nasty little problem hiding in this circuit, a real hidden danger that we have to deal with. And that brings us to Section 3, resetting the transformer.
So just think about this for a second. Every single time that switch is on, we're pumping energy into the transformer's core, building up that magnetic field. But what happens to all that energy when we suddenly slam the door shut and turn the switch off?
Well, the problem has a name: magnetization current. See, a real-world transformer isn't perfect. It's got its own internal inductance. So when the switch is on, this little bit of current starts building up. And if we just cut that current off instantly, that collapsing magnetic field is going to create a massive, and I mean huge, destructive voltage spike right across our switch. You can see it in the graph. It would kill that component in a heartbeat.
So how on earth do we fix this? Well, you can kind of see the evolution of the idea. The first, kind of clumsy fix is to just stick another power supply in there to clamp the voltage. It works, but it's not pretty. A better idea is to add a whole third winding to the transformer, just to catch that leftover energy. But the truly beautiful, elegant solution, use that third winding to not just catch the energy, but to actually funnel it right back to where it came from, the input.
And that elegant solution brings us to our final section, putting it all together. We're going to look at the finished circuit now with our clever fix in place and talk about some of the real-world trade-offs you have to make.
And here it is, the complete forward converter in all its glory. Let's take a quick tour. Over on the left, there's our main switch that feeds our transformer in the middle with its primary and secondary coils. And on the right, you can see that buck converter output stage we talked about. And notice that extra little coil up top? That's our hero, the third winding, the reset winding, that solves our big magnetization problem so elegantly.
So let's really watch what the current is doing. During that on time, the current in the primary coil is actually two things combined. It's the current going to the load, plus that pesky magnetization current. Then, when the switch turns off, that magnetization current gets smoothly handed off to the reset winding, and it safely ramps all the way back down to zero, getting the core ready for the next cycle.
But of course, as with all things in engineering, there's no free lunch. This design has some trade-offs. For one, your main switch has to be rated for a voltage that's way higher than your input. The number of turns you put on that reset winding actually limits the maximum duty cycle you can run at. And the big one? You have to make absolutely sure that the core's magnetic flux gets back to zero every single cycle. If it doesn't, the core will saturate and your whole converter is going to fail.
As circuit guru Sam Banyakov says, the solution is to dump this current back to the input to sort of reset the transformer. It's not about throwing that energy away. It's about recycling it in a really clever way that both protects the circuit and makes the whole system possible. It's just beautifully efficient.
And that just leaves us with one final thought. The forward converter takes an idea that seems totally impossible, sending DC power through a transformer, and makes it not only possible, but practical, all through some really clever circuit design. So it makes you wonder, doesn't it? What other impossible things in electronics are just waiting for one more elegant circuit solution to become our new reality?